Hey everybody, let's talk about scientific notation. Basically, you have a number greater than or equal to 1, but less than 10, multiplied by 10 to the x, where x is just any whole number. So for 10001, we can rewrite that as 1.0001 times 10 to the 4th. What about 0.0123? Well, that's just 1.23 times 10 to the negative 2. So how did I figure that all out? Well, here's a trick. Find the decimal place in 10001. It'll be right there. It is in front of the last digit. How many times do you have to move it to the left to make the number greater than or equal to 1, but less than 10? 1, 2, 3, 4. Looks like it's 4 times. So, therefore, we get 1.0001 times 10 to the 4th, because we moved the decimal place 4 times to the left. Now let's look at 0.0123. Well, how many times do you have to move that decimal place to the right to create a number greater than or equal to 1, but less than 10? Well, let's count. 1, 2. Looks like it's twice. So we get 1.23 times 10 to the negative 2, and that 2 comes from moving the decimal place to the right twice. And that negative sign is just there because we moved it to the right. So if your number is greater than 1, like this number right here, then your exponent will be positive. If your number is less than 1, for example, this number right here, then the exponent is negative. The number of times you move the decimal will determine the number, and the size of the number will determine its sign. So greater than 1, positive, less than 1, negative. So let's talk about significant figures, or commonly known as sig figs. This is a very important concept in chemistry. Significant figures tell us the precision of a measurement, or how accurate it is in a way, in common language at least. You can think of sig figs as the number of digits with a few rules attached. So normally we look from left to right. And then we start counting the digits when we come across a non-zero digit. So let's look at 0.0001000 meters. Well, let's count from left to right, and let's start counting the digits when we come across a non-zero digit. So I'm going to go like this. Ooh, first non-zero digit. So let's start counting the digits. 1, 2, 3, 4. Okay, so for every 0 to the left of 1, we do not count. So these can be ignored. But we can count every 0 to the right of 1. So we're going to count these. And why do we count these? Well, even though these are zeros, I'm talking about these zeros, they still matter, because the fifth zero, let's see the fifth zero, 1, 2, 3, 4, 5. The fifth zero, for example, tells us that we know for certain that the 100,000th place is a 0. That's the 100,000th place, by the way. So 0.000100 meters has 4 significant figures. 1, 2, 3, 4, as we counted before. We can rewrite it as 1.000 times 10 to the negative 4. And to count the sig figs in scientific notation, just look at this first number. And as expected, this number has 4 sig figs. Alright, now let me erase this for a second because it's kind of messy. And we'll look at another example. Sorry, it's not going to be fully erased, but we should be fine. Now let's look at the number 100. Well, in the laws of sig figs, we can count the 1, but we cannot count the zeros after 1. Well, wait a second, didn't I just tell you that you could count the zeros after the first non-zero digit? Well, you see, without a decimal place in front of the third zero, see how the missing decimal place there? We cannot tell for sure if the second or third zero is precise. Think of the decimal place as the green light to count the zeros after a non-zero digit. So, oh, that looks weird. That looks like we have 1,000, but it's actually just 100. So let's just keep the 100 there. So think of the decimal place again as the green light to count the zeros after a non-zero digit. Now, this can be written as 1 times 10 to the second, which can be written as 100, and yet 1 times 10 to the second has only 1 sig fig. So 100 has 1 sig fig. And what about 100 point? Well, this has 3 significant figures since the decimal place is there, and the decimal place tells us that we can start counting the zeros after the first non-zero digit, since it's like a green light to count all the zeros to the right. This number can be written as 1.00 times 10 to the second, and you see this number has 3 sig figs. So, now that we got rid of the left-sided and right-sided zeros, what about the zeros in the middle? Well, if we have something like 1001, we're going to count the zeros in between 2 non-zero numbers. The only exceptions where we don't count the zeros is to the left and to the right if there's no decimal place. But if there is a decimal place, then we do count to the right, and we include all the zeros. So it's kind of hard to take in. Just take notes and try to understand it and internalize it. I promise that it will be easier the more you practice. And because of the decimal confusion, like this one right here, where, there could be a decimal there or there could not be a decimal there, I usually like to write my numbers in sig figs because it makes it more clear how many sig figs there are, since all you have to do is just look at this first number right here. So let's do one example. So let me erase a part of the screen so I can write that down. Let's look at this number, 0.0212039. Just a random example I made up. Well, how many significant figures are there? Well, let's start counting at the first non-zero number from left to right. So 2 is the first number we count, and then we move all the way to 0 at the end. Well, why do we count the 0 at the end? Because there's a decimal place, and decimal places are the green light to let us count all the zeros to the right. And so if we count these digits, we get 1, 2, 3, 4, 5, 6, 7. So let me undo all that. Sorry for the confusion. So this number right here will have 7 sig figs. Not too bad. You could do more practice on your own using online sources if you wish. So let's do some measuring now. So if we want to measure something, we want to know how accurate the measurement is. This is where significant figures, as SEF for short, come into play. If we use a standard meter stick, for example, and know for sure that our rope is in between 1.1 and 1.2 centimeters, we can be certain about the first two digits. So let me draw a rope, let me draw a ruler, and let me just cut off this rope a little bit. Let's just say that the rope is in between 1.1 and 1.2 meters. So the third digit is uncertain, but judging from the ruler, we can say that it is about 1.16 meters. So when we do measurements, we can go one extra digit beyond what we are sure about, as long as it is reasonable. But we can't go any more than that, or else we are claiming to be much more precise than we actually are. So if we have, 1.1 and 1.2, we have a number in between. We can go one extra digit ahead and take a guess and say that using reasonable assumption, we can say that it is 1.16. So that's our extra digit that we add when doing measurements. In other words, we are adding one extra sig fig to our answer, to what we already 100% know. It just makes numbers more precise, but not so precise that it would be considered a lie. Let's try two examples. Would it be reasonable to read, let's just say we had this electronic scale and we had a piece of mass on it, and let's say it said 1.020 grams on the scale, on the electronic monitor. Would it be reasonable to read 1.020 grams from an electric scale and add an extra sig fig like 1.0203? Well, no, because where did you get this 3 from? That's just like a complete guess. It's not a reasonable assumption, so we keep it at 1.020 in this case, and we don't add an extra sig fig. Now, what about if you were reading off a mark on a volume, let's just say, and let's just say that the volume was in between 1.02 and 1.03 milliliters. Based on your judgment, you could say it's maybe 1.023 milliliters, and that would be absolutely okay because you added an extra sig fig within the realm of reason. Now, we got lab procedures out of the way, so let's talk about mathematical operations and how they relate to sig figs. So on to our next slide. When you multiply or divide two numbers, your final answer will have the same number of sig figs as the number with the least sig figs of the two you multiplied or divided. Now that's kind of a mouthful to take in, but let's just do some examples. Let's do 1.002 times 2.10. Your calculator will spit out 2.1042. But we can't keep all these digits. We limit ourselves to the least number of sig figs out of the two we multiplied. So since 1.002 has 4 sig figs and 2.10 has 3 sig figs, then our final answer will have the lesser of the two, which is 3 sig figs. So our final answer will not be 2.1042, but it will be 2.10 with 3 sig figs. Now, I didn't just cut off 4 and 2. No. What I did was that I took the third sig fig that I had, which was this 0, and I rounded it off. So this 4 right here, since it's less than 5, I rounded it down, and thus it was, 0. So, in other words, I rounded this number to the hundredths place, right here. And since 4 is less than 5, I rounded down, and that's why it's a 0 and not a 1. Now, let's say that we added or subtracted two numbers. Well, there is a rule for this. When you add or subtract two numbers, your final answer will have the same number of decimal places as the number with the least decimal places of the two you added or subtracted. Now, it's easier to do than to say, so let's take an example. 1.200 minus 0.2312. Well, my calculator spits out 0.9688, but we have to limit the number of decimal places to the least of the two we subtracted. 1.200 has 3 decimal places, and 0.2312 has 4 decimal places. So we choose the lesser of the two, which is 3 decimal places, and our final answer will be 0.969. Note how I rounded up since the 4th decimal place is 8, so it goes up, and thus this is a 9, as shown right there. Now, the next topic might be advanced for some people, because if you've never seen a logarithm in your life, you'll have no idea what I'm talking about. So I recommend you watch some videos about logarithms and anti-logarithms, or exponents, if you don't know anything about them. Well, let's now talk about logarithms and natural logarithms, log and ln. Log is usually base 10, and ln is just a log with base e, which is about 2.718. We'll also talk about exponents, or antilog, or inverse log, or I don't know. People call a lot of names, anti. So count the sig figs of the original number. The log or ln of the number has that many decimal places. Let's do an example. ln of 0.203 will be negative 1.595. And since 0.203 has 3 sig figs, then our final answer will have 3 decimal places. Weird, right? Well, this has 3 decimal places incidentally, so we are good. Now, what about the antilog, or antilog, or exponents? So let me just erase this work and show you an example of an antilog. So let's talk about what an antilog is. When we talk about an antilog, we're basically talking about exponents. Since if log base 10 of x equals y, if we want to get x from y, we are basically finding the inverse of it. So using our knowledge of logarithms, we know that 10 to the y is equal to x. So we are plugging in y to get back x. That's the inverse of plugging in x to get in y. So exponents is the anti, or the inverse of log. So antilogs are basically just the base of the log or ln raised to the number. The base of the log or ln raised to the number. So let's try to do sig figs for antilogs after I erase all this stuff. It's going to get a little messy, so I'm going to use the color orange. We know that's just the color we just used. I'm going to use green. So count the number of decimal places in the original number, or the number we are going to take the antilog of. The antilog of that number, aka 10 to the number, has that many sig figs. So let's just take an example. What is 10 to the 5.102? Well, your calculator will tell you 102,801.6298. Now, we don't want this because we need 3 significant figures in our answer, because this number right here has 3 decimal places, so our answer has to have 3 sig figs. So it's kind of the opposite of log in terms of the rules, if you think about it for a moment. Well, we can't just say that our answer is 103, because that's completely wrong, because 102,801 is much larger than 103. So how do we solve this dilemma? Well, I like to always do something called scientific notation. So let's write this in scientific notation with 3 sig figs. So that will just be 1.03 times 10 to the, let's move our decimal place, 1, 2, 3, 4, 5, 10 to the 5. So let's try another example. So let me just do some fine erasing once again and use a different color. This time I'll use black. What about 10.00 to the 5.102? Do the two decimals after the decimal in this affect the number of sig figs in our final answer? No. We only care about the exponent when it comes to scientific notation, aka the number of decimal places in this case. So our answer will still be, as before, 1.03 times 10 to the 5, because 3 decimal places in the exponent translates to 3 sig figs in our final answer. So note that when we have 3 or more numbers being multiplied, divided, or whatever, we follow the orders of operation, PEMDAS, parentheses, exponents, multiplication or division, and addition or subtraction. There are many great sites to practice significant figures, so use those to your advantage. I hope you learned a lot in this video. That's all for now. So I decided to attach an extra problem in order to show you how to properly do a question involving PEMDAS. So let's start off by simplifying this problem based on PEMDAS. And what PEMDAS is, that's parentheses, that's exponents, and these two are multiplication and division, and these two are addition and subtraction. So when you do order of operations, you want to follow the order of this acronym from left to right. So let's start by doing P, which is parentheses. So let's start off by doing 3.00 minus 0.993. So if you type that into your calculator, you get, let me see, you get 2.007. But we want to make sure to follow the laws of significant figures. So if this has 2 decimal places and this has 3 decimal places, we want to do the lesser of the two, so we are going to keep 2 decimal places. So our answer will have 2 decimal places. So instead of erasing the 7 and writing 2.01, we are not finished with the problem yet, so we do not have to simplify all the way. So what is usually done is that there is a marker that is kept to tell us what decimal place or what sig fig that we are at. So in this case, I underlined this 100th place because I know that this answer can have only 2 decimal places. And I'm not going to simplify right away because you can only simplify right away once you're done with the entire expression. But we've only gone through like maybe 2 of the 5 numbers that are present. So therefore, we are going to use this line as a placeholder in order to remind us that there are 2 decimal places, and we are just going to use 2.007 in our calculator, and eventually, once we have to deal with the sig figs, then in our final answer, we can start erasing. But right now, let's not erase just yet. So now let's do the second parentheses. So in here, we have the natural log of 3.99 plus 101, but we need to simplify the natural log of 3.99. So 3.99 has 3 sig figs, so when we simplify this, our answer should have 3 decimal places because that's the rule for ln. So if I type in ln 3.99, I get, let me use a different color, 1.38379. And we need 3 decimal places, so let's just underline 3. Remember, we are not going to start erasing digits just yet. And you might be wondering, well, how do I know how many digits I should keep after the sig fig that I just underlined? Well, I usually like to keep 2 or 3 extra digits after the sig fig that I identified. So for example, in this one, I went 2 past the sig fig that I needed. And now let's add 101. So if I add 101, I get, well, let me just add it, plus 101. I get an answer of 102.384. So when we're adding, we look at the decimal places. This has 3 decimal places, and this has, well, 0. So our final answer will have 0 decimal places. So let me underline that. And look at that, I went 3 past the decimal place because it's 3 digits after the last sig fig that I underlined. So now that we simplified the 2 parentheses, let's start doing some multiplication division because that's all we have left. So let's look from left to right. So we are going to multiply 2.007, remember to underline the 0 to tell us how many sig figs there are, and we are going to multiply this by 102.384. So let me just multiply that. 2.007 times 102.384. My answer is 205.485. So since this has 3 sig figs and this has 3 sig figs, our final answer will have 3 sig figs. So let's just underline that to tell us where our limit is. So our last step is just to divide by 3.11. Since we've already simplified all of this, all we need to do is do that. So if we divide this by 3.11, we get about 66.1. Now you might have realized that I stopped adding extra digits, and the reason is that we've reached our final answer. So we can just square that and we are done. Now you might be wondering, why am I adding extra digits beyond the number of significant figures? Well, the reason is because when we're doing this, we want our answer to be as accurate as possible. So if we started rounding off at the beginning, like we just didn't include any of these extra digits, then we would be losing a lot of accuracy. So instead, we round off all the way at the end in order to be more accurate. And when we round off at the end, we are still following the rules of sig figs because we kept track of the sig figs throughout the process in order to make sure that our final answer has the right number of sig figs. So all in all, by rounding off at the end, we are increasing the accuracy of our final answer. Because if we round off at the beginning, if we decide to round off all these numbers, this number, this number, this number, and that number, we would have lost a lot of accuracy. But by rounding off at the end, we save accuracy. So that's the true end of this video. Have a nice day.